thank you very much for attending this talk and the workshop. I hope you will have fun. My name is Luis. I sell shoes for a living. Not really. I do work for someone that sells shoes. And today we're going to have this talk about some reliability patterns. Before we go into that, let me give you a little bit of context. As I said, my employer, they sell shoes. I moved there around 5 years ago, but it feels very good to be back home. I'm Portuguese. It feels very good to be home. Because some things are really different. The weather is different, the food is different. But some other things, they never change. So I'm going to focus on things that I'm pretty sure that everyone went through. I'm going to start by asking all of you, and please just raise your hand and just throw it. What do you think this is?
Okay.
Hockey stick. Any other takers? Anyone thinks this is not a hockey stick? It is a hockey stick.
It could be a smoking pipe with some tobacco.
Very good. I'm going to use that one for the next. But it is a hockey stick. What about this one? What do you think this is?
Bitcoin.
I'm also going to use that one.
It's an ops engineer performance cliff.
It's nothing special, actually. It's just a monitoring graph, and it shows a peak of something, right? And for the sake of this example, let's assume that it was a burst of requests per second, for example. And the reason why I asked first what that was, because their shape is very similar. And we call this hockey stick. And why is this important? When these things happen, when such a traffic burst happens in your systems, and I'm sure that if you run stuff in production, you already went through this, sometimes bad things happen, right? Cascading failures, everything stops working. And then it takes a lot of human work to get those things back into production. Today, the patterns that I'm going to go through in this talk, they are not complex, they are not even new, they are quite old. But I honestly believe that we all did some of the things that I'm going to show. And I'm also going to share how we believe that you can improve the reliability of your systems without just throwing money at the problem with capacity and those things. So this is the most basic example that I could come up with to show what I honestly believe that we all did sometime in our careers. Maybe we are still doing it now, and it's fine. It's a very simple call to a remote procedure from an API. This is just a Java example, Spring framework, but it could be in any other programming language. You have a pattern, but the important part here is this is very optimistic. It just makes the remote procedure call and expects to get something in return. And as we all know, this is not always the case. Many times, for reasons that are completely outside of our control, this call is going to fail. And what do you think usually happens when our code is just as basic as that? Well, the most common pattern is that we just throw an exception to the application. The user that is using this particular application just sees an error message, if he's lucky, or he just gets a 500 server error and that's it, right? And we can definitely improve this. And these are the patterns that we're going to apply. We're going to build on top of this example and improve it step by step. So the first step is really, really very basic. And let's take just one of the hypotheses for this call to fail. When we made a call to a load balancer to a certain API, the instance that was assigned to the load balancer service request was in that moment overloaded, it failed. But there is a really strong chance that if we make the same call immediately again, that same load balancer then picks another backend instance which will successfully serve our requests. And if that one also fails, because some of those instances were also overloaded, if we try yet again, or yet again, we are increasing a lot our chances of succeeding that call. Obviously, we can't retry forever, but we can retry, and we should retry, to increase our chances of succeeding it. But obviously, this approach is very naive, for one particular reason. The moment it fails, we immediately try again. And if that one fails again, because we basically took one CPU cycle to do so, or a couple more anyway, and then we retry again. And if the whole fleet of our target was all overloaded, we are making matters even worse because we are immediately exploding the throughput. So it's not very smart, and we should do something about that. Not only that, let's consider for a bit, this is an API call, and this is just catching any kind of exception. But what's going to happen with this call if the target returns a 404, for example? This is considered an exception by the client code. So what it's going to do is going to retry again, but there's probably not many good reasons to retry a 404. Retry is going to return again the 404, and if we try 10 times, God forbid, then you get 404 10 times. You just make again matters worse. And this is important to understand. Retry, yes, it's good, but it's not to be done always. And this is when we should retry. We should retry whenever we detect a network failure or an overload situation. So not for every exception, for some particular ones, and these are called transient faults. Transient faults are those that, depending on the language, the framework, we know that they happen now, but they will be gone shortly. And these are called the transient faults. So, because this is very dependent for the programming language and the framework, I'm just going to summarize it with, now we only retry if this is a non-transient fault. Okay? Because it will be up to your particular implementation to figure out if this is a transient fault or it's not. Now I'm actually going back to where I started before, by mistake, which was, when it fails with a transient fault, we're going to immediately retry again. And this doesn't help. This will actually make matters even worse. From an overload situation, it will completely trash it. And this is actually a thundering herd problem. So it would be great if we could delay between each attempt. For example, instead of just immediately going and retrying again, we could consider sleeping for 10 milliseconds, 100 milliseconds, 200 milliseconds, which would be better already. This is better than the current implementation. The problem is that systems always find a way to align themselves to explode everything. And if all of our instances with the same application code, they all had the same delay for the same 100 milliseconds, somehow they would all align to try, stop for 100 milliseconds, and then they would all retry after 100 milliseconds, and then fail again, and then they will all try after 100 milliseconds. And this is what would happen. And this is very similar to the original problem, because they are somehow synchronized to destroy the target at the same time, because this is triggered by a common failure at the target that happened at the same time. So one way to overcome these problems would be something very similar to this. And the gist of this approach is that it will retry, and between every retry, it will delay for longer. So the delay is not a static value that we define up front. It's rather, on the first retry, try it relatively fast because of that typical scenario that we hit an overloaded instance. But if we try relatively fast, but not immediately, we may get another one that is not overloaded, and maybe we succeed. But if not, then we actually start backing off, and we start increasing this delay. And ideally, in this function, in this shape, which is an exponential function. So we start backing off for longer and longer and longer after each retry. But we also don't want to grow this function forever to infinite, or a very large number. So basically, we also want it to stop at a maximum reasonable time to wait, because you need to remember that before this, there is a customer using your application, and you don't want him to be waiting forever for your target to eventually recover. This is how it could be implemented. Again, just some example code. The difference from the previous iteration that now, while waiting, it calculates from the retry number, and it calculates an exponential function to decide for how long. But you can also see a new element here, which is the second problem, where all of the instances will retry at the same time. It introduces a random component. So it waits for that amount of time, which is the function, but it also has a random delay. And this random delay is the one that is going to solve the problem of all of the instances retrying at the same time. So you have to remember to seed your random generator. That's the only thing that you have to think about. So usually these libraries are going to be smart and do it for you. So now we have a nice retry strategy. We know what transient faults are. We are backing off. But by the way, I didn't mention the name. That's the fancy name that this pattern has. It's truncated because it ends at a value that you define. Don't wait for longer than this number. Exponential backoff because it's exponential function. And with jitter, the jitter is the random part. But what happens when what started to be a transient fault lasts for so long that it's no longer a transient fault? When transient faults become permanent faults. Well, what eventually is going to happen is that you stop serving requests, because what we are doing now, you are repeatedly trying, retrying. It's a transient fault. It was classified as such, which means for every request, you just make your customers wait for longer, for the exponential delay, for the amount of times that you will try, for a prolonged period, like that example, which is not realistic at all. Something that we found on the internet. And it's also not desirable, because maybe there was something that we could do that could handle this situation. And the situation is basically when you can detect that a transient fault is lasting for long, maybe we could do something else. And it exists. It exists. It's the circuit breaker pattern. Raise of hands who heard about the circuit breaker pattern. Good, great. Some of you not raise your hands, which means the next 42 slides are for you. No, they're not really 42. So first, this pattern was actually made popular by Michael Nygaard in the book Release It. If you never read it, go and buy it, it's awesome. It's like the second Bible after the SRE book. But anyway, so what is the circuit breaker pattern? It's exactly the problem that we just identified. So this pattern is going to allow your application to stop repeatedly doing an operation that we can already predict that it's going to fail again. Interesting, right? It sounds like magic. And it achieves this in a very simple approach. First, a circuit breaker is just a proxy in your application code. You are effectively calling the circuit breaker, asking it to execute the operation on the target, and then the circuit breaker makes the call. What it's going to do is that every time that it calls the operation on the target, it's going to keep counters of the successes, the failures, well, actually the failures, counts of the failures, and it's configurable so that when it detects a certain amount of failures, it does things. And it does these things by keeping states. So it has three very important states that we're going to describe. Let's start with the most typical one, the one that you want to have, which is going to be the closed state. And when the circuit breaker is in the closed state, it's just a proxy, so it just forwards the request to the target. As simple as that. Everything is fine. I'm so proud of these animations. Right? And again. This is how it works in the closed state. It just forwards the request to the target. But eventually, the target becomes unhealthy. And when the target becomes unhealthy, it just drops your request. And this returns an exception to the application. And it increases the failure count. So this happens again. And it increases further the failure count. And the important part is that when it reaches the configured amount of failures, consecutive or otherwise, because this has many different ways to be configured, it's going to change the state. And it changes the state to the open state. So in the open state, it does two important things. The first one is that if there is an attempt to perform the operation, it immediately returns an exception to the application. The good part. And it also starts a timer. before I go into the timer, the good thing that by opening the circuit, let's go a little bit back, we were retrying, we were always hitting the target. These things also don't help if for 10 minutes we are retrying a lot. So by opening the circuit and not actually hitting the target, we are being nice and we are giving it enough time to recover from that overload situation. And this can stay open for that duration, which is that timeout. This timeout timer that starts immediately as it opens does something interesting, which is, well, now we don't want this to be closed forever, because this helps us to recover automatically. So I think I have more animations. I had one animation, but there is one animation. It drops immediately. Sorry. Right. So as soon as that timeout, the timeout timer expires, it's time to try something different. And it switches the state to the half open state. The half open state, it's special just because it's neither open, it's neither closed. What it's going to do is only a selected amount of those requests are actually going to be forward to the target, while others are still going to be dropped. Yeah, dropped. And this is the important part. Only a selected amount of requests are going to be forward, others are still going to be dropped, so your edge throughput is not going to be forward. And why is this important? Because eventually, when these succeed, your circuit breaker just detected that your target recovered. And because it recovered, it is going to close the circuit breaker again. And then we are back at the first step. And your application is behaving as normally again. And this is actually pretty cool, because it helps you without human intervention. And it detects those things, it's nice to your dependency, and it recovers automatically, and it's completely up to you how to fine-tune these parameters, but it's just helpful. And it's even more helpful because of that particular state, the open state. In the open state, if you remember, it immediately returns an exception to the application. And you may be wondering, how is this good? This is where we started. Right? The exception was happening, and now we are in the same situation. We are failing fast. But actually, failing fast is the last pattern, and it's probably the most interesting one. So you had this situation where you had that target, you needed to do something, make that API call, it's failing, and now you are timing out and waiting, making everything slower. And now we are failing fast. And what can we do while failing fast? And now I have this metaphor. So open your mind, because I'm going to try to map this into this remote procedure call. It's a very simple piece of code. And if you see here, there are some circumstances of failure in this piece of code. So take, for example, the remote procedure call is the division operation there. And if that thing to the right is invalid, it would fail. But we ask ourselves the question, when that fails, what do we do instead? And it's actually the most important question that you need to do. What do we do when that fails? Because now we have the benefit that we immediately failed. We immediately failed, and if we ask ourselves this question, now in advance, like you do when you do unit tests. When you do unit tests, you try to cover all of the scenarios. You're very proud of your coverage, and you're sure that every possible value was tested. But when we do the remote procedure calls, not so much. We are a bit more optimistic, and we don't protect ourselves, our systems, from all of these possible failure scenarios. So by doing that, when calling the remote procedure call, you will ask yourself a lot of interesting things. Most of them are even product questions. What do we give out to our customers when that thing didn't work? And now I have this example of a complete fake website with a complete fake t-shirt. And I want you to pay some attention on that part, which is highlighted at the bottom. It says delivered by Adidas, right? It's fair to assume that this website, when it was composing this page, it made a bunch of calls to different systems, And for the sake of the example of this fake website, it's called a fake API of some partners that returns the name of the partner, Adidas, and the URL for the page, a catalog page for that partner, for example, a fake catalog page. So, if you remember our example, if we make that call while composing this page and we fail to get the name of the partner, what do you think would happen in the very optimistic approach? Probably that we just failed to show the page and this is fine, or is it? It's not fine at all. It's not fine at all. Because this means you just lost a sale. You could have sold that nice fake t-shirt, but you didn't. You didn't because you couldn't provide something like is Adidas is selling this, right? Very simplistically, if you ask yourself the question, what do I do instead when I can't get the URL and the name of the partner? Well, why not just return a string that says delivered by a partner? It's probably even legal. You are still putting the disclaimer that someone else is selling this, just couldn't provide the name or the URL. But remember, this was temporary. The system is going to recover, half open, eventually comes back. Only a small amount of customers saw that. And if they even try to reproduce it, it's already working. So maybe even legally you could get by. But this is just one very good example on how powerful this question can be. What do we do instead? This simple question at the time that we're writing the code allowed you to fall back to something that is reasonable, and now you still make the sale and increase the stock of being figured out. So this could be how this thing could look. It's probably code that doesn't compile. I hope it does. It would be something like this. You ask the circuit breaker to make the call, write with the retries, and if that fails, then you just provide a fallback, which could be another function call, or it could be just a static value. Actually, the interesting part with the fallbacks is that you can be very, very creative on what you